Hello everyone, welcome to Course Edit. So last time we discussed about this verify epsilon delta function of our C++ library, which we are going to complete after this course. So for this lecture, we have to first check what was wrong in our code. So here you can see I have changed few things. From that we just did to square root L plus epsilon minus C. So why did we do this? So at first we have your error which we had. So actually while I was explaining, I took an example delta equals to 1 and in the flow, we just took everything based on that. So instead of taking delta as delta, we took delta as 1 for x plus 2. So what you can do, you can just rewrite the function, which was your 0 less than your x minus 2 less than delta. And similarly, you have this. So basically, let's not keep this x minus 2, keep this x minus a. And you have this fx minus L. So you know what your limit was at fx? It was basically your x square. So at x equals to a, L equals. So basically at x equals to a, you'll have your limit x tending to a, fx equals to your, basically not limit fx. So the limit was basically your this fx plus h. Basically you don't have to take this limit, you just have to take fx only. So basically the limit was your so this was your limit, which was I think your x square. So it'll just become a square over here. So we'll have this a square over here, and then you have this limit. So basically this was your 0 less than x minus a less than this delta. Then you have fx minus L mod less than your epsilon. So let's say we have this, these both functions. Then what you can prove with x minus a, you can just say that x minus a is less than delta. For obviously, if you remove the mod, you can remove it in two ways: x minus a greater than 0, x minus a less than 0, where you'll have x less than a, and here you'll have x greater. Let's say you have this equal sign as well. Then you can say x greater than equals to a. And for this, you have x less than a, and you have this x minus a negative is less than delta. Then you have your x minus a greater than delta, which is basically only possible if you. So basically, this is possible only if you have this x greater than a. But since we have x less than a, this is not possible at all, because delta was supposed to be greater than 0, if you remember it correctly. So we can say this x minus a has to be greater than 0 at least. X minus a has to be greater than 0, which is not possible with x less than a. So this is basically not possible. So this condition you can just remove, and then you just have this condition, which was your x minus a less than delta, and then you can have your x plus a. So basically this you get, which is your correct equation. You can just verify this from here as well. And for x plus a, you can just write x plus a equals to x minus a plus 2a. Then you can just write x plus a is your a function which you can just have like x plus a is less than delta plus basically this will be equals to x minus a plus 2a, which is your less than equals to less than your delta plus 2a over here. So you have this. Let's say we have a equals to 2, then you have your delta plus 4 over here. So let's not worry about that at all. So we have this. Now what we can do, you can just sorry if the speed is a bit fast, because we have to complete many topics, so we have to go at this pace. So you have this delta plus 2a, then you have this epsilon, which was your x plus x square minus a square. Sorry, not a square. What was your L? Sorry, it's a square only. So you have this mod, which is I think less than your epsilon. Then you have x minus a mod times x plus a mod. So basically there will be some 2a value as well over here, and you can just finally say that mod of x plus a is less than your delta plus 2a. So you have all this. Then you have, well, remember that this condition is valid because of this condition, so we have to consider both, then finally we'll get this only. So for this we have this epsilon, then we can just, then what we can do, we can just say that this is actually delta times delta plus a, then we have this epsilon, then we can say delta plus delta square plus a delta minus epsilon less than 0. So it will be equal to this, because this delta is greater than these two things. Okay, so this won't be equal over here. So we have this less than epsilon. Since delta can be a bit, a little bit bigger than that, so it might be able to get equal to epsilon. So we can just say that this will be less than equal to 0. And we can find both the roots of these functions. So they will be basically delta of your, let me just write. So to find the roots, you can just use your this quadratic formula for roots, obviously. So you had delta equals to your minus of this b, which is your a, I think, over here. Wait, I'm definitely doing something wrong. Okay, so this was plus 2a, not plus a. Then you have this plus 2a, 2a delta. Then you have this plus 4a square. Sorry, minus 4a square. This was minus, sorry. So we have minus b, which is your minus 2a, plus minus under root of b square, which is your 4a square, minus 4ac. 4a square minus 4ac, let's say 4 times this, 4 times minus epsilon. So we can just write plus 4 epsilon. And then we have divided by 2, which is your 2 times a, which will be your like 2 times 1. Then you have this minus, so you can just, let's say, you can just simplify this. You can just write by 2 plus minus under root of 4a square by 4 plus 4 epsilon by 4. So you can just cut all, you can just remove all that. And then at final, and then finally you have this minus a plus minus under root of a square plus epsilon. Then you can just say delta equals this. Then you can just put this over here like delta 1 times your, sorry, not delta 1, delta minus, let's say alpha 1. Suppose if alpha was the root, was the root, then you can say alpha 1. Then you also have your delta plus alpha 2 less than epsilon. So suppose if I say that you can not take alpha 2 as your delta, why do I say that? Because you have this condition over here that delta has to be greater than 0. Suppose if you take minus a minus a square plus epsilon, then the problem is that this delta, let's say alpha 2. So basically this is a value for delta only, so let's call it delta 2. So we have your delta 2 greater than 0, but this is not possible over here. So we'll just ignore this, and then we can just directly write minus a plus of 4 plus, sorry, not 4, not even this, minus a plus of your under root of a square plus epsilon is actually less than 0, I think. Sorry, it's not actually less than 0. It's basically, we have this. Then you can just say that this this is your delta 1, which is your this. So basically this you'll get as your final delta. So obviously this has to be less than equal to, and we found this, and this root finding is actually on your, what do we say that? Yes, so basically it's on your this basically what I want to say, it's basically based on your equal sign. So let's use our wavy curve method to find your final solution, a final answer. So let's say we have this delta 1 over here and delta 2 over here, then we can just say plus minus plus. Then obviously this has been excluded, and also it has to be less than, so we can just take these things. Then what do we have left? We are left with this final stuff, delta 1. So basically delta 1 is your so basically delta 1 is this basically sorry, not delta 1. Delta has to be greater than your this. Delta is greater than this your delta 1. So you can just write it is greater than minus a plus under root of a square plus epsilon. Since we wait, it is greater than or less than, so let me just check over here. We have less than equals to 0. We have this minus sign. So basically delta is your greater than this, not less than. Basically this from here to here. So what you can write, delta 2 less than delta less than equals to your delta 1. So the final verdict which you have, like the greatest value for delta is actually your delta 1. So you can just take delta equals to minus a plus under root of a square plus epsilon. So the maximum value at which it won't have any problem, or the worst value you can say, is this minus a plus under root of a square plus epsilon. So basically in our case we just use c over here for constant. So you can just replace a equals to c, then minus c plus under root of c square plus epsilon. So we have all this, and you obviously know what your c square is. Basically this a square was your limit, so you can just write your limit over here. So you can write minus c plus under root of limit plus epsilon, and this has to be your obviously minus c only. So delta equals to this. The worst delta you can say is equal to this. Well, obviously delta can be less than this, but maybe what if this delta 2 is greater than this delta? Okay, so I did wrong over here. Delta 2 is actually smaller over here, so let's not complicate it. So delta 2 is your this, and then you have your not included symbol, then you have this included symbol of yours. So you have this final verdict. So basically this will work now for every, I think, all this function. And don't take power 1 by 2, because power function basically gives you an integer value. So if you take power function over here, and if you do like power of L plus epsilon comma 1 by 2, that will give you a 0 over here always. So that will always give you a verification successful code, so which will also be a problem, because you'll get always a delta which is your 0. So please don't do that. And obviously you have a question for this function over here. Suppose if you are given a discrete function, fx equals to your x square for all x not equal to your this, let's say x not equal to your 2, and it is equal to 5 for x equals to your 2. So you just have to prove this, that limit does not exist at x equals to 2. Basically for the same values you just have to find you have to just modify everything over here to just write a function which just helps you in getting this, that it'll just give you a verification failed answer. But suppose if I just try to run this, let's say we do f2 over here and x minus l, it will just return true, because we haven't added any like statements, conditional statements, where it just shows that for a discrete function just calculate it according to the function. So since we didn't do anything like that, we can just say that it won't work in this case. So this function verify epsilon delta is still incomplete. And if you have any doubts, you can obviously come to courseader.doubts and then you can log in. And then what you can do, you can just post a doubt, ask a question over here. It doesn't require any fees. It is like zero fees over here to ask the question, at least for a few months. Let's say for 3 months we have this. You can come to this and then ask the question. I'll be there to answer your query, right? I think it will take 24 hours only to answer your query. So please do go and check out the doubts platform of CourseEdit. So we can also say that this is not complete yet. So yet it has to be modified by us. So let's go to the next topic now. Obviously, you know what continuity is. I don't have to explain that, right? Basically, if FA exists, if this exists, FA exists. If FA exists, if limit fx x tending to a exists, and also you have this. If this exists, and if your function limit x tending to a fx is equal to your fa, then you can say that this function is continuous. Obviously, if it doesn't exist at fa, if the function doesn't exist at fa, you can just say that this is a discrete function or something like that. Undefined function, obviously, at a. So it won't be continuous as the function doesn't exist over there. And if the limit doesn't exist, then it was never continuous. It must have gone something like this, crazy stuff. Basically, this discrete function shows that this was going like this, and then it suddenly took 5 over here. And then we are back to this track. So just check that as well. So we have this completed as continuity is also done. Don't worry about continuity. We don't write much function in continuity for now. So basically after this we can just come to the proof of derivative. So last time we just proved that fx. So basically it was your fx derivative of x to the power n by dx is equal to your nx n minus 1. Now let's say we never proved this for our negative. Suppose if n was negative, obviously n has to be whole number for now. Obviously we will be also taking it as p by q, don't worry about that. So for that we'll be just proving chain rule as well. So for now we just have this n less than 0. Let's say we have to prove it for this. Let's try this right after this. So we have this dx to the power n by dx, which is equals to your let's say I don't want to do this. I actually want to do x to the power n. So x to the power minus n. N is obviously greater than 0 for now. So we have this x to the power minus n and n greater than 0. So the power is actually your negative number. So we can just say x to the power n. Obviously you can write x to the power minus n equals 1 by x to the power n. This is like the basics of basic. So this can be written as your d by dx so basically you can just write like x to the power minus n equals something which is relevant to our x to the power n. Well, let me first see how much we have done. Oh, so we have completed only 90 minutes. We are left with much more time. So don't worry about that. We'll be just back with I'll be just back in a few minutes. So come back. So we are, I think, at this negative proof. Yeah, so basically we can just write this as x to the power minus n. Obviously, if you remember the reciprocal rule, we can just directly do it with that, and then we can just later prove the reciprocal rule after this, and obviously the quotient rule also. So let's prove it just by that. So the rule says that if there is a function that is like this, let's say we have gx, let's say it is equals to x to the power n, and we have a reciprocal function 1 by gx, which will be your this, which you can say is this, which is your negative power obviously. So we can just say that it can be written as gx by g dash x. Basically this is your derivative for fx, which was your this fx equals to x power n. So we can say this is your g dash x divided by gx square. So after doing this, what we can do, you can just write the derivative of x to the power n, which was your for natural, not natural. Yes, so for now we just have natural or natural numbers only. So we have this n as your natural number, and let me just say n belongs to natural number over here. And then we can say that d of x to the power n is basically your n times x power n minus 1. Basically we proved this with that expansion. So that expansion didn't prove negative because you know that coefficient, or basically the combination of anything, the factorial, basically it does not exist for negative numbers, so you can just say that so you can just say that it just doesn't exist for this complete equation as well. So that's the reason derivative doesn't exist for now. I mean, it exists, but we haven't proved it using anything. So we are just proving it using quotient rule, and then later we'll be proving the quotient rule itself. So basically you have this as your dx to the power n by dx, and let's say we have this gx square now, x to the power n minus 1 divided by x to the power n square over here, which you can write as okay, so you can just I think, okay, so we have to take minus over here. I'm sorry, I forgot that this is there has to be minus n as well. Basically I missed this. So you have this, you can write it as minus n by this dfx by dx, d of fx by dx. Then you can write this as your minus n x to the power, since you know that n square is your this won't be an n square. Since we did for the gx, then we took the square outside, it will be like x power n minus 1 minus 2n. So you'll get minus n of this minus times x to the power minus n minus 1. So if you see it clearly, you can just say that this minus n, if we take it as m, so this is basically your mx to the power m minus 1, which is again f dash x equals this, which is actually very similar to your n x to the power n minus 1. So you can say that it works for negative numbers as well. So let's try proving quotient rule, or we can just first prove everything like that power rule works even for power rule works for every real number n, but not for x equals 0. Basically you know that it won't work for x equals to 0 because let's say we have a negative power, then we can say that 0 to the power negative 1 is basically your 1 by 0. You can just write this, and then you can write this, then you can write this. So this will basically disprove it. Basically not disprove it, this will create some tension between our work. So I don't want any kind of problem in that. So this is your complete definition for power rule. So if you want, we can just prove this right now, or let me just check how much we have studied. Okay, so we have studied for 25 minutes. We are left with multiple more minutes. So let's try proving this for, I think fraction would be good. So let's say we have a fraction. Let's say we have this. Basically your x to the power m by n, or let's say p by q, x to the power p by q. So what you can do, you can just write y equals this. Well, we'll be using chain rule directly without proving this, proving the chain rule. So we'll be proving chain rule as well afterwards. So this is your this, and then you can just write y to the power q equals x to the power p. And obviously you know that in a fraction, like p by q belongs to a fraction, then you can say p comma q belongs to integer, and q not equals to 0, and obviously there's nothing else. So you have this y to the power q equals x to the power p. Then by chain rule you can say you can write y to the power q minus 1 times q, and then you can write dy by dx equals to your x to the power, basically you'll be doing x d times x to the power p by dx, which will be actually your p times x to the power p minus 1. So let's calculate this. Y, let's say dy by dx, which is your y dash, the first derivative of your this function. So you have this p of x to the power p minus 1, p of x to the power p minus 1 divided by your q times, basically your y was I think x to the power p by q. So you can just insert that right after we write this over here. So after insertion, we can say that p to the power x times p minus 1 divided by q times x to the power p by q times q minus 1 is basically equals to your p times x to the power p minus 1. So instead of writing all this, let me just directly solve this. So we can just take p by q over here, and then we have this p minus 1, then we have q times q, which will be your pp. So basically p will get eliminated from over here. Then we have this. Yes, so we are left with this, which is again basically if you write your p by q equals n, you can say this is again n x to the power n minus 1. So it's now proved for your this natural number, whole number. So let's prove for whole number as well. It's like for all natural numbers, it's proved. So for whole numbers, it is like natural number plus 0. So what you can do, you can just write that your p, sorry, not p, x to the power 0 d times x to the power 0 by dx is equal to your let's say we have is equal to 0, basically d of 1 by dx, it should be equal to 0. So you have this d times x to the power n by dx equals n times x to the power n minus 1, which you can write directly as 0 times x to the power minus 1, which is your 0. So you have all this. Let's prove this for our that, what do we say, irrational function. Sorry, not function, irrational number. So we have this irrational number, which is your let's say we take a smaller example, which is I think, let's say pi we take. Let's just take for example we have this pi. We'll just take an over here later. So if you remember this logarithm and exponential stuff, then you should remember that this x to the power a can be written as e to the power a ln x, and obviously you know the constraints on x and all. So the constraints are basically that it has to satisfy this. So e to the power x, and obviously you can't take x equals to 0. Obviously you can take x equals to 0 for n greater than 0, but you can't take x equals to 0 for n equals to 0 less than equals to 0, because it will create some problem. So you have to remember these conditions according to these number system sets. Basically for natural number set you have to remember that you have this and this, so you can remember it that way, or you can always try proving this. But I would recommend remembering that because we'll be using it later at many places. Anyways, so we have this x to the power a equals e to the power x. Sorry, not e to the power x. I think it was a ln x. So we have this. So this is basically an identity. So let's say we have so obviously from here you can just prove by the expansion and all if you want, and basically we so we have all this, and then we have this irrational function as well, sorry, irrational number as well. So let's prove it right now. Well, obviously if you try to think as a programmer, then you will say that we can't write x to the we can't write this x to the power pi as this x times x pi times. But as a programmer you can think that instead of inventing a special algorithm, we can just always reduce everything to two functions, which is this and this. So instead of doing this and this, we can just reduce it to e to the power a and then ln x. So we have these two functions, and these two functions will help us to like denominate what we need. And suppose we want to solve this, then we obviously have to learn exponents and logarithms. Sorry, exponents and logarithms. I am not even able to speak logarithms now. So let's finish this right now. I've actually been preparing this for 4 hours, and then I just had to record it fast enough to like make it a 35 minutes or 30 minutes long video. So thank you everyone, thank you for watching, and don't forget to ask your doubts on doubts section. So basically this is your doubts.coursereader.com. so you can come over here and then you can just log in. So you'll be able to access the doubts only after you log in. So you can access this interface, but you won't be able to like watch the chats of other people. Okay, so there is no chat for this one, but we have chat for this epsilon function. So we wrote everything over here. Then we had some talk with some Mr. Panda over here. Then we had all this. So it was a great conversation. So you all can just come over there and ask your doubts. Thank you everyone for watching. So let's meet in the next video or the next lecture on, I think, Thursday. So yes, thank you everyone. Thank you for watching. Please go to the doubt section, I would say, because it's good for like asking doubts with your colleagues. So thank you everyone. Thank you for watching. It's already 34 minutes. I should quit.